In this video, we are going to talk about the IV characteristics of the bipolar junction transistor, the BJT. And because we have three terminals here, we expect to see more than one IV curve. So we'll have more than one curve for the IV characteristics. The most important one is the one that we are going to start with, which is the characteristics, the curve between the collector current IC and the voltage between the collector and the emitter VCE. We'll focus on the NPN transistor again, and as we said for the PNP, what we are going to do is exactly the same curve, but you need to reverse the direction of the current, and you need to change the voltages from VCE to VVEC, VBE to VVEB. You change the two letters of the voltage, okay? So we are going to work on the NPN transistor, and the possible setup to study this curve between IC and VCE, a possible setup is to connect the transistor in this setup, like connecting the emitter to ground, the base to a current source where we are going to change the value of the current source later, and then we study the relation between IC and VCE. As we change VCE, what will be the value of IC and so on. This is for a fixed value of I base. And then we change I base and we repeat the experiment again. We try to sketch the curve between VCE and IC for a different value of I base and so on. So for each value of I base, we try to plot a curve between IC and VCE. Okay? So let's start by saying that we talked about the active region. We said that in order to be operating the active region, we need the base, the emitter base junction to be forward, and this is guaranteed by usually VBE in the range of 0.7. Usually between 0.5 to 0.7 in order for this junction to be forward. And we need the collector base junction to be reverse, or at least, as we said, at least not forward. And in order to guarantee that the collector base junction in the NPN transistor, we are focusing on the NPN transistor, the collector is N and the base is P. In order to guarantee that the collector base junction is not forward, you need to guarantee that the voltage between the base and the collector is less than 0.5, because usually a junction or a diode, they start operating around 0.5, starting from 0.5, and then when it operates full operation, it reaches to 0.7 or 0.8. So it starts to operate at 0.5. So if you guarantee that VBC, the voltage between the base is P and the collector is N. If you guarantee that the voltage between the base and the collector, VBC, is less than 0.5, less than or equal 0.5, then you guarantee that this junction is not forward, okay? And you guarantee the operation in the active region. So let's see the condition translated to VCE. So in order to be in the active region, assume that this is by default. Assume that we have a current source here. This current source will guarantee that this diode between the base and the emitter is forward bias, it's on. So by default, this condition is satisfied. VBE is satisfied because we have a current source that forces a current of the base to flow between the base and the emitter, and hence the base emitter junction is forward. Let's focus on the other one. In order to guarantee that our transistor is active, you need VBC to be less than or equal to 0.5. Okay, VBC equals what? You can say that VBC, if you look at the transistor, VBC can be written as VBE minus VCE. You need VBE minus VCE to be less than or equal 0.5. You can prove this easily. VBC is the same as VBE minus VCE. Why is that? Let's do it quickly just to convince you. VBE minus VCE. VBE is VB minus VE minus VCE is VC minus VE, right? So if you expand this, it will be VB minus VE minus VC plus VE. This will cancel with this. So the result will be VB minus VC, which is VBC. So VBC can be written as VBE minus VCE. So VBE is already 0.7 because the base emitter junction is forward biased. Minus VCE must be less than or equal to 0.5. We can take VCE to the other side and we say that in this case VCE must be greater than or equal 0.7 minus 0.5, which is 0.2. This means that in order for the transistor to operate in the active region, VCE must be greater than or equal to 0.2 volt. Of course, this 0.2 volt is approximate. Usually there is a value here, we call it VCE saturation. This is the point at which the transistor will move from being active to saturation. Based on our calculation here, if we assume that the base emitter junction has 0.7 and in order for the other junction to be off, it has to be less than 0.5, VBC has to be less than 0.5, we calculated VCE saturation here to be 0.2. So this is VCE saturation. But VCE saturation in general can be something between 0.1 to 0.3. The value of VCE saturation, the edge between the active region and the saturation region, we call it VCE saturation. Usually it is something in between 0.1 to 0.3. Based on our assumptions here of 0.7 and 0.5, we found it to be 0.2. Okay? So if VCE is greater than or equal to VCE saturation, you are in the active region. What happens if VCE is less than 0.2? If VCE is less than 0.2, this will lead that VBC will lead to that VBC is greater than 0.5, which means that the base collector junction will start to be forward, okay, and the transistor now worsens the saturation region. So if VC is greater than 0.2, remember that, greater than VCE saturation, whatever I give it to you, it can be 0.1 up to 0.3. If you are greater than this value, you are in the active region. Less than this value, you are in the saturation region. In the active region, if you fix I base, then the collector current will be beta I base. So for a certain value of I base, let's say 60 microampere, the collector current will be 60 microampere multiplied by beta, right? It will be constant. If you change I base, if you increase I base, the collector current is going to increase. If you decrease I base, the collector current is going to decrease. Always it will be beta I base. So for example, this is 40 microampere for I base, this is for I base 60 microampere and so on. But if I base reaches zero, this means that the base emitter junction is now cut off, right? Is now cut off. So if I base reaches zero, IC also will be zero because the base collector junction, the collector base junction is already reversed, right? In the active region, we are already reversed. And when you reduce I base to zero, the emitter base junction will be also not forward, or you can say reverse. The base current is zero, then the emitter base junction is not forward, it's reversed. And the collector base junction is also reversed, then we say that the transistor at this line here, it's cut off. So the transistor, if I base equals 0 in our case here, I base is 0 and the collector base junction is reversed. In this region, the collector base junction is reversed. Then the transistor will be cut off. Okay, what happens if VCE goes below, VCE saturation goes below 0.2? We said that if VCE goes below 0.2, VBC will be higher than 0.5, which means that the base collector junction will be forward, and thus you expect that when the collector base junction is forward, there will be a current that will flow from the base to the collector in this direction. But the collector current was coming down, and now you are going to feed some current up, right? So that you expect that the collector current is going to decrease because it was going down, the collector current, and now once this junction becomes forward bias, there will be a current going up, some holes or some positive charge going up, which will decrease the total current of the collector. So that once you enter the saturation region, you will find that the collector current is going to decrease sharply like this. because you are feeding now, once the base collector junction becomes forward biased, there will be a current going from the base to the collector, which will reduce the current of the collector, okay? It will reduce it until it reaches 0. If you increase the forward bias more between the base and collector, the transistor is going to reverse its operation. The base, the collector, and the emitter, they are going to reverse operation, which means that the transistor is going to operate in the reverse active or inverse active region. Reverse active region. So if you increase or if you decrease VCE more, then VBC is going to increase more. If you decrease VCE more, VBC is going to increase more, which means that the collector-based junction now is more forward than the emitter-based junction. So the transistor is going to reverse. The main current will be coming from the collector, and the current of the emitter is going to decrease, and the collector current is going to reverse direction. It will be going up instead of going down, and the transistor operates in the reverse active region. We don't care very much about this region, don't worry, but the most important part is here. In order to be in the active region, VCE must be greater than VCE saturation, which is usually between 0.1 and 0.3. And in this case, the current of the collector will be approximately constant, okay, equals beta I base, depending on the value of I base. In fact, or in practice, you will find that these curves, and we'll discuss this later, these curves will not be horizontal. There will be a little bit of a slope. We'll discuss this later. And also, in practice, you will find that at a certain point, the transistor is going to break down and the collector current is going to increase rapidly like this. But again, this is outside the focus of our course. This is just for your information that after a certain limit, the transistor is going to break down and IC is going to increase quickly. Okay, the same thing applies to the PNP transistor, but instead of VCE, we use VEC. And you keep in mind that IC now is not entering the transistor, it's going outside the transistor. We'll discuss the next characteristic curve in the next video, inshallah.